Okay, welcome to EGR 550. In today's class, what I'm going to do is I'm going to work out uh, the problems, and these problems will be from the end of the book. So I would strongly recommend that if you have the textbook, please check out these problems. That way, you know what problem I'm looking at. The first problem that I would like to solve is from the end of chapter, problem 2.12. So consider a system that is given as the state equation x dot is equal to x1 plus 2 x2, x2 dot is equal to minus x1 plus 2u, wherein x1 and x2 are state variables and u is the input. Now, if the output is given by 2x1 minus x2, then we want to find out how can we write this system in a state space form, and then how we can find out this system maybe differential equations form, or what is the order of the differential equation. So writing this equation in the state space form is fairly simple. So you have x1, x2, this is d by dt, and you have x1, x2, and then what we need to do is we need to fill in the blanks. So first thing is this will be 1, 2, minus 1, 0, plus this will become 0, 2, and this will be u. Now the next question is, how do we write the output state variable? So output is going to be y is equal to x1, x2, and this is going to be 2 minus 1. So once we do that, we have the system written in state space form. Now the question is, what is the order of the system? Now, one thing you have to remember, that even though these equations are two equations in first order, which means single dot. So two equations in first order, which means the total order of the system is second order. Second order system. That is something that you should keep in mind. Even though the order of the equations is first order, the system itself is the second order system. Now, the next problem which I want to talk about is something like the linearization and Taylor series approximation. So I want to talk about next problem, which is 2.16. The first problem is determine derivative of d by dx x and sine of x. Now I want to emphasize on what this means. So, and there is an important distinction here. So imagine you are driving a car. Okay, imagine you are driving a car, and behind this car you have a parachute. So what's going to happen is, as this car is going forward, there will be resistance. Now I want you to visualize the second scenario wherein you have this car and now this car goes in this direction. Clearly the parachute would inflate in this direction. So what that means is the drag force. So the drag force on the parachute is always going to be opposite to the direction of motion. Now typically, if you have a drag force, you would see drag force equation Fd is given as a constant c multiplied by v square, where v is the velocity. The problem here is, no matter whether your velocity is positive or negative, whether velocity is positive or negative, your drag force is always going to be positive. Now this issue may not look important, but it is, because drag force is always going to be opposite the direction of velocity. And unfortunately, the analyst or the engineer has to write down this explicitly when we draw the free body diagram or when we write the equations of motion. Now, what is the difference when the same equation, please understand, this same equation is expressed in this fashion. If you have the equation expressed in this fashion, please understand the magnitude remains the same, but the sign is preserved. So imagine that now your drag force, so if your velocity is 5, your drag force is x, norm of x is going to be 25. If your velocity is -5, your drag force is going to be -25. So in other words, the sign or the direction of the force is captured. But the problem here is, how do we take the derivative of this guy? Does anyone know how to take the derivative of a sine function? SIGN. So because in one of the problems that we are going to solve, we will have this type of function. So nothing serious, you just have to use the chain rule. So d by dx, which is x norm of x, is equal to, so what we have to do is we have to use the UV rule, dx by dx plus, then you are going to have x d by dx of norm x. And if you look at this equation, oh, this becomes 1, and this guy is sine of x. So this becomes x multiplied by, so here there will be norm x 1 plus norm x. So this answer is 2 times norm of x. So if you take the derivative, this is what you get. So remember this, we will use this while solving the problems. The next part is what I want to do is linearize about operating point and 3x cube norm of x dot square. So how do we linearize these three? So if we want to linearize this, so this is going to be the Taylor series expansion. So d by dx of 3x cube plus the value of the delta x. Let me write the Taylor series expansion first. So Taylor series expansion of f of x is f of operating point x bar plus df by dx, this value at x bar multiplied by the variable delta x. So let's substitute 3x cube at x bar is equal to 2 plus df by dx, which is 9x square at x bar is equal to 2 delta x. So this becomes 12. So 24 plus 36 delta x. So this is the linearized equation. Now let's try to do this for linearization of norm of x. So this is one. So f of x is equal to norm of x or absolute value of x. Now once you linearize, this is going to become x bar is equal to 2 plus d by dx of x delta x. Delta x by x is going to be the sine of 2. It's not the so magnitude of 2. So this is going to be 2 plus d by dx of delta x is going to be the sine at x bar is equal to, is the sine at x is equal to 2. So this is the sine, and the sine is positive 1 multiplied by delta x. So the linearization is going to be 2 plus delta x. Are you with me so far? And the last part is, what is the Taylor series expansion of x dot square at x bar is equal to 2? Can someone tell me? So it's going to be d by dx of x dot square plus delta x plus x dot square at x bar is equal to 2. So here is something interesting. When x bar is 2, which means x is constant, this x dot is going to be 0. This guy becomes 0. Now here, when we are going to take the derivative of this, the derivative of this x dot is going to be 2 x dot x double dot, or 2. Actually, this I need to write this. I need to explain this in a better way. So now, side note, this is d by dx of dx by dt square. This guy is going to be 0. So the total solution is going to be 0. Now the next part, I want to actually work out a problem is, so this problem is problem 2.18. So in this problem, what we have is, we have this system. There is the external velocity v1, and this is velocity v2. So this is nonlinear quadratic damping. This is system. So this is a nonlinear damper, and this nonlinear damper is exerting some force. This force is c v2 minus v1 square. So this is basically the relative speed. So we have to first find out an analytical expression Just bear with me for a second. For some reason, Zoom dropped out. Okay, and we are back. So second thing is we have to provide an appropriate linear model. So the question is, how do we linearize this system? And how do we create an appropriate linear model? So to do that, first and foremost, we need to set up the differential equation of motion. So the differential equation of motion can be written as using the Newton's second law. And if you look at the forces on the right hand side of the equation, so forces are given as force multiplied by displacement is equal to work done. So I can write this down. Work done is equal to Fi x plus F naught minus y is going to be equal to 0. So for arbitrary x, this is going to be in the equilibrium. So what we are going to do is, we are going to write this down. Fi x is equal to F naught y. That gives you the spring force diagram. Now in this case, what we have is, in addition, so this is the spring force. But what we have is, we have damping. So if you look at the problem, the force is given as C V2 minus V1 square. And to account for the direction of damping, I would use the sine function, which is V2 minus V1. So this equation can be written as C V2 minus V1, and then I would add the norm of V2 minus V1. So this is how the damping force can be expressed. The next part is, how do we write the linearization? So this will become minus 2, and I'm following the results that we obtained some time ago. V2 minus V1 multiplied by V2 hat minus V1 hat. And when V2 minus V1 is equal to 0, then clearly the damping force is going to be 0. So 0 damping. So if you have a system like this, so how does it account for a system which has a nonlinear damping? So this is the nonlinear damping. And you have this spring, which is a linear spring. So if you combine these two, and if I give you this mass, for this system is going to be mx double dot minus 2 v2 minus v1 norm of v2 minus v1 plus k x2 minus x1. Wherein x2 is the displacement of the support, x1 is the displacement of the support. So that is how you will solve these types of problems. Now with that, we are able to attack a slightly harder problem. So we can attack slightly harder problem. So I'm going to work out the homework problem, which is problem 2.21. So in problem 2.21, what we have is we have an air circulation fan system. So this fan has an induction motor. This has a fan. There is this air in and this is air out. So this is in, this is out. Then here, this is the speed omega. And just like in the previous problems that we talked about, this fan is gonna have a motor torque, and there is going to be an impeller attached to this fan, and there is going to be some inertia. So tau, and there is W, and this impeller has the inertia G. Now the first and foremost thing is the system equation is given to us as J omega dot plus B omega plus D omega omega is equal to tau. Now this equation, first we have to derive. So this is the first part, derive this equation. The second part is if the motor torque is given as wherein tau bar is the steady torque and tau A is a small amplitude, then we have to actually linearize the model about the steady state operating system. Now I need to explain to you what that means. So in last class, we talked about the linearization. Now this linearization could be about a fixed point, or it could be about constant motion. Now, what do I mean by fixed point? So fixed point is, think about that you have a pendulum and we want this pendulum to be linearized about 0, 0. So 0, 0, which means displacement is 0, theta is 0, and theta dot is 0. Theta is 0 and theta dot is 0. So this is linearized about fixed point. Now the second case is same pendulum, and imagine this pendulum is swinging. It's going back and forth, back and forth, back and forth, back and forth. So this pendulum is swinging. And what I want to do is I want to linearize this pendulum about this swinging motion. So for an example, if I were to plot this swing, this motion is going to look like this. And what I want to do is I want to find out if I perturb this pendulum, if this pendulum is swinging, and if I hit it, what would happen to the motion of the pendulum? Would it go back, or uh, would it save? It go back to original system. So would it continue to go back to the steady state motion that it had, or it would become completely unstable? Now I want to ask you this question because this is sort of a theoretical question that is important. Now in case A, everyone understands we are trying to find out the motion of this pendulum about this fixed vertical point, which is 0, 0, where this displacement is 0 and velocity is 0. Now imagine that on this pendulum, this is like a grandfather clock. This is the pendulum of the grandfather clock. And this is sort of oscillating back and forth, back and forth. And if you attach or if you hit it with a hammer, so if you hit it with a hammer, what would happen? What do you think would potentially happen? Any suggestions? You can unmute yourself and then quickly tell me what you think would happen. So if you look at this thought exercise, two things are possible. As long as this force imparted by the hammer is very small, then you would see some small perturbation about the motion, which means it kind of go here, it will kind of go here, and finally it will settle down to where it started. But if you are going to hit this motion hard, then basically there is a possibility that the pendulum, which was upside down, will kind of get inverted. And clearly that is completely out of the controlled steady state motion. So the idea here is this perturbation or this external disturbance has to be small, because if this external disturbance is large, then clearly that will destabilize the system. And if you read the problem statement on problem 2.21, this guy is a small fluctuation. Are you with me so far? So what that means is if you have this small perturbation, only then the analysis that we are doing can be performed. So what I'm going to do is I'm going to start with this simple analysis, and we will try to derive these equations of motion, and then we will perform the linearization. And I would be honest with you, when I studied linearization for the very first time, I really did not appreciate the power of linearization. But as I started working on the practical systems, as I looked at the real life systems, control problems, then I realized that linearization is actually a very powerful tool, uh, because the systems that we study in actual practice or system that we control in actual practice are nonlinear, and we do not have complete understanding of nonlinear systems yet, because nonlinear systems can exhibit different type of behavior in the different operating range. So what do we do? What we do is we choose the operating range where the system is operating, perform the linearization, and use linear control techniques to analyze, or linear analysis technique to analyze. So what that means is, even though the motion may be nonlinear, but if you take this teeny tiny part, if you take this teeny tiny part, if you take this teeny tiny part, then system can still be analyzed and solved as a linear control system. And that is the beauty of linearization. So with that, I'm going to start with the first problem, part A. That let me draw the free body diagram of the system. So there is this external torque, there is speed, and then you have this damping. This damping is actually, there are two types of damping. One is a linear damping, and the other one is the non-linear damping, omega. So this is the linear damping. And then this is the non-linear damping. So using Newton's second law, J omega dot is equal to the external torque. So this equation is torque is equal to J theta double dot. This is external torques, and these are the inertial forces. So this is F is equal to MA expression. But theta double dot is, now I'm going to represent this as J times omega dot, because d theta by dt, which is equal to theta dot, is equal to omega. Now, something subtle, but I just want to tell you that this equation is in the second order form. But by changing the variable, I converted this equation into first order form. Now, some of you may ask me, what is the advantage of this? The advantage of this is, if you have an equation in the second order form, if you want to solve it, you are going to need two initial conditions because you will have to integrate twice. But if you have a system that is given in the first order form, then you only need one initial condition. That is the difference between the first order form and the second order form. That being said, let's add the damping terms. Oh. So this will be minus b times omega minus d times omega sine of omega. So this equation now becomes j omega dot plus b omega plus d omega like this. Now what we need to do is, we need to perform the steady state analysis. So what happens at steady state? At steady state, tau is equal to tau hat with sine omega t. Tau will be 0, fluctuations in omega will be 0, and rate of change of omega, which is d omega by dt, is going to be 0. Substituting this, in equation 1, you are gonna substitute all these values. This guy becomes 0, and you would get 0 plus b omega bar plus d omega bar square is equal to tau. With this, we can solve d omega bar plus b omega bar minus tau is equal to 0. This is a quadratic equation. It's going to have two roots. So we can look at the roots. Omega bar is equal to 1 2d b square plus 4 d tau minus b. And then the last part, what we want to do is, we want to substitute all these values in the equation, and we already know that when we linearize, after linearization, if you have a system something like d omega omega hat omega sine omega, that gets converted to 2 times norm of omega. So what that means is I can rewrite this approximation in the very first equation that we have here. I can rewrite this approximation in the very first equation that I have here, and I would get j omega dot plus b omega plus 2b omega is equal to tau can be linearized as j omega bar plus b omega hat plus 2 times d times omega bar is equal to tau. So this is how you would linearize the system. So let me work out a few more problems. By the way, any questions on the problem worked out so far? So let me work out the next problem. Problem 2.22. Again, it's a similar structure that what you have is you have a motor, there is this flex coupling, then there is this pump. So the inertias are Jm of motor, P of motor is K and then here there is flow out. There is flow in, flow out. Now in this problem, Jp is the moment of inertia of the impeller. Capital omega m is the angular velocity of the motor. Capital omega p is the angular velocity of the pump shaft. K is the torsional stiffness. Now please understand that when the torque is transmitted, the torque has to get transmitted through flexible coupling. So we can say Tf is the torque that is transmitted to flexible coupling. So we are going to say Tf is the torque transmitted through flex coupling. And Q is the volume flow rate of the pump, which is Q over here, which is given as Vp times capital omega P. And with that, we will actually find out uh, the equation of motion. So first and foremost, we have to apply the Newton's law. Newton's law is given as J of motor capital d by dt of motor is equal to Tm minus Tf minus Bm capital M. Then Hooke's law is for the coupling. And Newton's second law and the output equation, which is for the flow output, is Q is equal to Vp capital P. So now we got these three equations, and somehow we need to write these in a state space form. So writing these equations in state space form, I would first choose the states, which is x input and output so state space model is x dot is equal to ax plus bu, y is equal to cx plus du, and we have these three equations, and I can write these vectors. A is going to be minus p over m by jm minus 1 divided by jm, 0 k 0 minus k, zero 1 0 0. So this is how that equation is going to look like. Now, one quick thing that I want to mention is these three equations are three first order equations. So the order of the system, so order is 3 because we have three first order equations. Now, if we want to linearize, then we can certainly linearize. So for that, here is the second part of this equation or the problem. He's saying Tm, which is the torque that is supplied by the motor, is given as maybe with this equation where A times S Vf square divided by 1 plus S divided by SB square. Now SB is nothing but the slip. So 1 minus capital omega m divided by omega s. So this is called as slip. Now Vf is the magnitude of voltage. So if we want to linearize, then what we need to do is we need to linearize Tm. And to linearize Tm, now this Tm depends upon multiple factors. So Tm is the function of capital omega m, capital omega s. So if you want to linearize this, the linearization would look like Tm is equal to partial Tm partial m. So dm plus partial Tm partial s ds. Now I would like to discuss the physical interpretation of this equation. What is so physical interpretation? Now let's start with linearization. So linearization is simply nothing but is the linear approximation from point A to point B. Linearization is nothing but linear approximation from A to B. Now, wherein what you have is you have X and you have Y. Where X is the independent variable and Y is the dependent variable. Now imagine a case where rather than just one line, you have a surface. So think about it, like you have Y and it depends upon X and it depends upon Z. And now what you have is you have this surface. So Y has two independent variables. This is one independent variable and the second one is other independent variable. So what I want to do is I want to perform a linear approximation. So the linear approximation in this case is going to be change in the Y is equal to slope of Y with respect to X multiplied by change in the X. plus slope of y with respect to z multiplied by change in the z. Now I want you to think about the same thing here. Change in y is equal to slope of y with respect to x. But since this is a single independent variable, we have a full derivative multiplied by change in the x. And I'm going to write this down. Change in y is equal to slope of y with respect to x multiplied by change in x. But since there are these two variables, change in y is equal to slope of y with respect to x multiplied by change in the x, and same thing for z. Everyone understood this? So what it means is, since there are two independent variables, so this is the first independent variable, this is the second independent variable, we want to perform the Taylor series expansion. This expansion needs to be written something like this. Now the next question comes is, how do we evaluate this expansion? So to evaluate this expansion, if you are mathematically inclined, you can use calculus, or if you want, you can use some online tool like Wolfram Alpha, you can use Mathematica, you can use MATLAB, and then find out these values. So this guy and this guy can be found out either by hand or using computer algebra. So just to show you, I'll just work out the problem partially. So what I did is I used MATLAB, and MATLAB can do it with a symbolic variable SYMS, and then I got these answers: partial TM by partial TM by partial sigma m, and oops, okay, I will do it again. Partial TM by partial sigma s is equal to partial Tm divided by partial s, because we have a slip variable here, which is partial s divided by partial sigma s, and partial Tm partial sigma m is equal to partial Tm. So I use the chain rule: partial s divided by partial sigma m. And since we are doing it at 0, I will have to do it at 0 initial conditions or 0 operating conditions. And once you use the MATLAB, you are gonna get this equation as partial m partial s square, and this equation as 1 divided by partial s. So the linearized equations are gonna take the form is, I will write this equation down: A equal to 1 divided by Jm partial Tm So Vs minus Bm, and everything else will remain the same. And I would encourage you to work out this math, and then you will realize that your answers, depending upon the what state variables you choose, may be slightly different. But if you use the same state variables, then you should get the same answers. So the next problem which I want to work out is an automotive system. So we have few more problems to work out. So 2.26, problem 2.26. What we have in this problem is that we have a car, and this car is traveling on this bumpy road. And for this car, suspension, and the road surface, the model that is given to us is this. So this is the model that they came up with. Here is the excitation ut. Here is the displacement, say x1, or you can call this x1, x2, and you have the velocities x1 dot and x2 dot. And I would just write this down like k1 b1, and then this is k2. And we have to derive the equations of motion and then try to analyze this motion. We can actually use a transfer function, or we can use some other, we can use the numerical integration, or we can use some other formulation using direct solution of differential equation to solve this problem. So any ideas how would we solve this problem from the students? Any suggestions, ideas, doubts, questions?
We can start with the free pipe diagram.
Pardon me?
Free pipe diagram.
Yes,
And
we have to draw the free body diagram. Correct. Now, but you don't have to reinvent the wheel. What I want to show you is, what I'm going to do is, this is shown in the vertical direction. I am going to turn it down and kind of put it in the horizontal direction. I'm going to put it down in the horizontal direction. And now my question to you is, does this problem look similar to the problem that we have worked out? Remember the problem that I worked out in class? The only problem there were two masses. Now there are three masses. Now what I'm going to do is, I would like to set up the equation the way we have set up for the two masses, and then just eliminate the masses. So what I'm going to do is, I'm going to do something like this. So bear with me for a second. I don't want this to be confusing, but I will try to be very clear in my discussions. So this is M1, this is K2, B2, M2, K3, B3, M3, K4, and B4. And if you recollect, here we have a mass matrix. Then we have a damping matrix. And then here we have a stiffness matrix. Now, can someone look at your notes real quick? And then here is U1, U2, and U3, where U1 is the force acting on this guy, U2 is the force acting on this guy, and U3 is the force acting on this guy. Can you quickly look at the notes that I wrote in the class and tell me if you observe any pattern in the equations that I wrote? Can you see the pattern in the equation that I wrote a couple of classes ago? I remember I solved this problem. I remember that I solved this problem. Remember this problem? This problem was solved in class. Any pattern here? Can you see any pattern? Can you track any pattern? Any suggestions from anyone? So human beings are very good in detecting the pattern. So I'll start and that will jog your memory. So this is M1, 0, 0, 0, M2, 0, 0, 0, M3. Here is going to be K1 plus K2 minus K2 minus K2, K2 plus K3. Then this is going to be 0, 0. This will be 0. This is going to be, this is going to be K2 plus K3. This will be minus K3. This will be K3 plus K4. And this will be minus. Same thing is going to happen here. B1 plus B2 minus B2 minus B2, B2 plus B3 minus B3, 0 minus B3, B3 plus B4. Now what we need to do is substitute. So I'm going to call this M1 and I'm going to call this M2. I want you to visualize there is this mass here. I want you to visualize that there is another spring here and another damper here, and treat this mass as 0. Okay, treat this mass as 0. So what you will have is basically you are going to have M1 and M2, M3 becomes 0, and then substitute the appropriate values of B1, B2, and B3. So what I'm saying is try to create a correspondence between this figure and this figure and substitute appropriate values here, and boom, that is the differential equation of motion for this problem. Any questions? I would encourage you to try this. And it's 2:18, so we'll take a break of 15 minutes and we will come back after the break. We pull the mass out and let it vibrate. So basically what happens is you get a sinusoidal displacement which decays. So this is called as the free response. But many a times what you have is you have an excitation force which is F cosine omega t that is acting on the system. So in that case, what you have is you have something called as the forced response. So force response. And total response comprises of free solution or free response plus a particular solution. And many a times when you have a forced system, if you have a damping, I want you to understand that this free response as time goes on is decays, which means the final response will be dominated by force response. So this is what you would see. What you would have is if you have a system that is subjected to forcing, then you're going to have initially the free response and then gradually there will be force response because the free response will decay. And this force response is actually the function of multiple things. It is the function of the frequency. It is the function of the amplitude of forcing. And it also depends upon whether there is a resonance taking place or not, which means is there any energy interaction where the energy from the external forcing or the work done by external forcing is exciting any of those systems modes or something like that. So depending upon what frequency we have, what damping we have, the system response could be varying. So those things that we need to take into account when we are trying to solve the problems. Now you will also come across the concept which is called as the convolution integral. Convolution integral is nothing but another way of finding out the response of the system. So basically what you do is you have something called as the state transition matrix that relates the old state with the next state, and you convolute, which is essentially you multiply and integrate that with the force response, and that will give you the total value or the total solution of the system. Next thing which I want to talk about is something called as the physical realizability. So physical realizability. So mathematically, you can write the equation for a system something like this. So you can have m x double dot plus kx that is equal to u plus u dot plus u double dot plus u triple dot. Now, if you have this type of equation, the key question here is this system physically realizable? Now, what do I mean by this? Which means, is it possible for us to build this system that can actually be physically made? So, which means, can I have a mass? Can I have a stiffness? And say damping is zero. Maybe damping is zero. Can I have external forcing u, u dot, u double dot, and u triple dot acting on the system? So even though mathematically this is possible, in physics or in physical system, this is not possible physically. And let me put this discussion into the perspective of transfer functions. So if I were to convert this system into transfer function, x is going to be my input. Sorry, x is going to be my output. And u is going to be my input. If I take the Laplace transform on both sides, this would look something like this. Derivative is replaced by s multiplied by the function s square multiplied by the function plus s cube multiplied by the function. Now what I want to do is I want to construct a transfer function xs by us, and this function would look something like this. And here 1 plus s square plus s cube. Here, as you can see, order of the numerator is equal to 3 because that is the highest order of s. Order of denominator is equal to 2. If the order of the numerator is greater than the order of the denominator, this system is physically not realizable, which means this system not physically realizable. Now, I would encourage you to construct such a hypothetical system or transfer function in MATLAB and try to run this and just check what happens. And you will get some interesting prompts from MATLAB. So even though mathematically such a system may be possible, this system is physically not possible. So one thing you should always check that the order of the numerator in the transfer function should be less than or equal to the order of the denominator. One thing also I want to point out is the stuff that we discussed about the stability is also super duper important. So stability is dependent on the eigenvalues of the system or the poles of the transfer function. Now the question is, sometimes the system may be stable, but if the forcing frequency matches with the natural frequency of the system could be still become unstable, which means the system response would become infinite. So what I want you to do is, I want you to kind of remember this. So if you have a system, mx double dot plus kx is equal to f of t, mx double dot plus kx, and this f will say a cosine omega t. Natural frequency of the system is square root of k over m, and omega is the frequency of external excitation. If omega is equal to, this is also called as omega n, system becomes, so system response becomes unbounded. System response is unbounded. So you would observe that the system response would kind of grow something like this. And this is pretty much the crux of chapter 2. So I would encourage you to go through chapter 2, and chapter 2 is intense in a sense, like the author has talked about the line graph, bond graph, and other techniques to solve different problems, but we haven't talked about it. We just talked about the two techniques. One is the linear analysis, non-linearization, then transfer function, and we looked at how to use Laplace transform to solve the problems. But if you were to look at some complicated systems like electromechanical systems, electromechanical and thermal systems, in that particular case, you will realize that you'll have to use some advanced modeling technique. And in that case, the bond graph and the linear graph sometimes may be advantageous. Okay, now what I'm going to do is I'm going to stop here for a second and move on to the next chapter. So at this point, if you have any questions, I would be happy to answer. So just a second, let me discuss the next chapter. So chapter 2 talked about uh, all the different systems, how to use these systems. So now what I'm going to do is I'm going to look at chapter 4. So bear with me for a second. Okay. Okay. The next chapter which I want to talk about is chapter 5. And in chapter 5, we are going to talk about something called as the performance specifications. So what do I mean by performance specifications? Performance specification means if I design a system, how do I want this system to behave? Do I want this system to achieve certain characteristics? Do I want this system to basically behave in a certain fashion? Do I want this system to be quick? Do I want this system to be sluggish? And all these parameters, they uh, are called performance specifications. So what are the main important parameters for performance specification? So first and foremost, we have to deal with something called as the speed of response, which means we want system to respond very quickly. Sometimes we want system to respond slowly because we want to dampen out the transient. Uh, we have to suppress the transients. Sometimes we are very interested in system to be stable, which means no matter what the disturbance is, system should reject the disturbance. But at the same time, let me tell you that in certain cases, we want system to be mildly unstable. So what do I mean by mildly unstable? So for an example, if you look at the F-16 or F-22 or some tactical aircrafts, they need to be super duper fast and they need to be super duper agile. In that case, the aircrafts are designed to be unstable because and the flight control system is actively stabilizing them because that would give us very high responsiveness in some tactical maneuvers. So even though we say stability is desired, in certain cases, we want system to be mildly unstable so it can respond very quickly. The next part is how accurate the system should be. Now, there is a difference between accuracy and precision. Accuracy is closeness to true value, and precision is repeatability. How many times we get the same value again and again when we perform the repetitive measurements. Now, there are two ways the system response can be described. One thing is you can describe the system response using time domain, and second is you can describe the system response in the frequency domain. So what is this time domain? In time domain, what I want you to understand is this is the system. If you look at this system is going up, then coming down, going up, coming down, and then kind of stabilizing. So this behavior where you have time on the x-axis and the response of the system is on y-axis, that is called as the time response. Now, in time response, what you have is you have different times, and this is very important. So I want you to notice on the x-axis, you have something called as TR. TR is called as the rise time, which is the time the system takes to go to the maximum possible amplitude. That is the rise time. Peak time is the time that it takes goes to the peak. So rise time is usually when the system response is about uh, the the desired system response, and the peak time is when the system response actually goes to all the way up to peak. So if your system input is 1, you want your system output to go to 1. So rise time is how far it goes, how much time does it take to reach the 90% And sometimes, again, depending upon what you are trying to see, in certain textbooks, they talk about 95%. So that is the rise time. And peak time is the time after the overshoot, the maximum time it takes to go all the way to the overshoot. Peak value is nothing but the amplitude at the peak. Percentage overshoot is nothing but the amount of overshoot divided by the steady state response. So amount of overshoot divided by the steady state response. And settling time is basically when the response, the final response is within 2% of the steady state output. That is called as the steady state response. Now, let's take a simple example. And what I want to show you is these are the equations that are given for the rise time, peak time, percentage overshoot, and the settling time. So you can use these equations to design the time response, and you can actually decide what should be the properties of the stiffness, what should be the property of damping, what are those individual values so that the particular response can be met. And here is one example that I'm going to solve in next class. But I just want to tell you one more thing, that the performance of the system can also be described in the frequency domain. So what that means is this is something called as the Bode diagram. In the Bode diagram, what you have is you have the gain on the y-axis, and you have the frequency on the x-axis, and then you have the phase angle on the y-axis, and again you have the frequency on x-axis. So the system performance can be discussed either in time domain, or the system response, system performance can be described in frequency domain. In time domain, the important performance specifications are rise time, peak value, percentage overshoot, time constant, and settling time. And I would derive the expressions for these values in next class. But what I want you to understand is, if you want to design a system, then somebody may say that design a system for certain rise time, design a system for certain peak time, design a system for certain peak value, certain percentage of overshoot, certain time constant, and certain settling time. Alternatively, the same system can be designed using the frequency domain specs, wherein somebody would say, hey, design me a system for certain bandwidth, design me a system for certain static gain, design me the system for certain resonant frequency, certain input impedance, and certain output impedance. And sometimes they also specify the gain margin and phase margin. And gain margin and phase margin are related to the stability. So the takeaway here is the system can be designed in time domain, and system can be designed in frequency domain. Now, both these concepts, the time domain and frequency domain, they finally are one and the same. Because what happens is the stability in the time domain is given by the eigenvalues, and stability in the frequency domain is given by the poles of the transfer function. So here is the basic idea. So if I were to draw the real part of the eigenvalues, or if I were to draw the this would be the imaginary part. So this is the imaginary part of the eigenvalues. And if I were to draw the real part of the eigenvalues, and if my eigenvalues are somewhere over here, what that means is I have this much amount of margin. I have this much amount of margin to play with before the system becomes unstable. So basically, I have this imaginary component here, and I can increase the gain by so much amount that I can keep on increasing the gain till these eigenvalues cross these imaginary line. And that is the basis of gain margin and phase margin. So how much gain can we increase before the system becomes unstable? And phase margin is how much phase we can increase before the system becomes unstable. And again, I would give you the precise mathematical definitions of gain margin, phase margin, and how to find gain margin, how to find phase margin using MATLAB in next class. But in this first class, as an introduction, I want you to understand that stability in frequency domain is similar to the stability in time domain. In time domain, the stability is governed by the eigenvalues, and in frequency domain, the stability is given by the poles of the transfer function. Now, the gain margin and phase margin is the margin or the amount of play that the engineers have to increase the gain or to change the phase till the system becomes unstable. So that is nothing but the amount of wiggle room that we have before the system becomes unstable. Now, in the last class, we talked about what are the different nonlinearities that come into picture. So we have saturation, we have hysteresis, we have limit cycle, we have the jump phenomenon. One thing that I want to tell you that the time domain specifications and the frequency domain specifications that we talked about, they help us design the linear system. So you cannot specify a time domain or a frequency domain specification for a nonlinear system. So basically, if you really want to go ahead and understand the system, or if you want to design the system for any particular specifications, the one possible way to do the system is design a system and make sure that that system is behaving as the linearized approximation of the nonlinearity. Because as we discussed earlier, the linear systems, we know everything about the linear systems. But unfortunately for nonlinear systems with these different types of nonlinearities, different types of saturation, jump phenomenon, hysteresis, the specifications that are specified by the linear analysis cannot be met. So if you want linear analysis to be used, either the system should be linear or you should linearize the system. Now, the next thing is, well, if you want to use the linear tools, we want to use linearized system. The other approach is don't exceed the linear operating range, which means almost all the nonlinear systems in the teeny tiny operating range behaves like a linear system. So make sure that even though the system is nonlinear, it is operating in a very limited range. That way the system behavior can be approximated as the linear system. Sometimes what we do is we add canceling nonlinearity, which means we have a nonlinear system, but we add some other nonlinear element that basically cancel the nonlinear behavior. And that is also possible. So you can use some type of linearizing element that would cancel or increase the linearity of the system. You can use a completely nonlinear feedback, which means you have the nonlinear feedback that canceling out the nonlinearity. Then the next part is basically limit the operating range. So basically the operating range is going to be limited where the behavior is going to be linear. Then limit operation over a wide frequency band. And this is something interesting. Many a times at a low frequency, the systems behave in a linear fashion. At high frequencies, the system behaves like a nonlinear system. Then we actually come up with some type of mechanical stops that would limit the motion. A classic example is the grandfather clock. Grandfather clock has a pendulum, but if you have seen the grandfather clock, there will be mechanical stocks that actually limit the pendulum angular displacement within certain range. You can also minimize Coulomb's friction, which is like static friction, or stiction, which is stickiness and friction, using some type of lubricant or lubrication that would minimize the nonlinear effects. Clearly, if you have backlash or gear coupling, that would also increase the nonlinearity. That's why you want to make sure that the backlash is minimum and the couplings that you use are linear or linearizable. So when we try to design mechanical instruments or mechanical systems, we have to specify few things for the instruments. First, we want to see what is the sensitivity of the instrument, which is the response of the system to the unit input, which is also known as the scale factor. So what is the output if you supply one unit input? What is the dynamic range, which means in what range that system will operate? I'll give you a very simple example. If you have a tire pressure gauge, you cannot use that to measure the pressure inside the internal combustion engine, because the pressure inside the internal combustion engine is varying very fast, and the simple tire pressure gauge will not be able to measure that temperature accurately. The next part is, what is the resolution? Resolution is the smallest value that can be measured by that instrumentation or that can be displayed by that instrumentation. Then what is the linearity? Whether that system is linear, whether the system is behaving linearly with respect to input, or whether the system can be approximated by a straight line. And that is nothing but the closeness of calibration curve. The next thing is, how do we want the drift to be? We do not want system to be wandering or drifting as time goes on. But unfortunately, all practical systems would have some amount of drift. So we need to characterize what is the full scale drift of the system. Then we need to know what is the useful frequency, in what range the system is going to work. Then we want to find out the bandwidth. What is the maximum frequency at which the instrument can operate, and what is the maximum frequency that system can respond to? And then we want to find out something called as the impedance. Impedance is the ratio of force divided by velocity. So whenever you have to assemble, so let me give you a simple example. You cannot attach a Hummer transmission to a Honda Civic engine. Why is that? Because the Honda Civic engine will not be able to drive Hummer transmission efficiently. So what that means is, if I want to match this engine to the transmission, I need to match the forces that are being transferred, and I need to match the velocities at which these forces are transferred. So that's what we mean by impedance matching. So this is a simple chart that shows you the linear approximation. This is the dynamic range in which the system can be operating. And as you can see, this is the straight line. This is the straight line that you see here. And the system response is actually nonlinear, but maximum deviation is shown as the linear approximation. From the linear approximation is shown over here. So this is the maximum deviation that from the linear approximation. So linearity is this change, which is delta R, divided by the full scale output, FSO, or full scale reading. Now, bandwidth is used in different contexts depending upon the different disciplines. So, but one interesting interpretation of the bandwidth which we will use is nothing but useful frequency range. So for example, if I have a sensor, can that sensor be used to measure input which is changing 1 times a second? Can this sensor be used to measure the input that is changing 10 times a second? Or can this sensor be used to measure the input that is changing 100 times a second? So, so CPS or cycles per second is hertz, and that's what is the frequency. Now, sometimes we have to design something called as the filters. So filters means basically you have a signal. That signal has multiple frequency components, and you can design a low pass filter which would only allow the low frequency components to pass. You can design the high pass filter that will allow the high frequency to pass. Or you can design a band pass filter which would allow frequencies in certain band to pass. So there is a low pass filter, high pass filter, and band pass filter. And again, earlier we have to design these filters by hand. Nowadays, we have fantastic MATLAB toolboxes that we can use to design the filter. And many a time, if you work with DCOM or digital communication, you have to be aware of the rate at which the information is coming, which is like called as baud, because digital communication is series of zeros and one. So how many zeros and one can be decoded without data loss? Why do we need to control the bandwidth? We need to control the bandwidth because our system needs to behave as per the specifications. So we want to have the maximum control uh, and at the range that the system is operating. We need to make sure the system can support the frequency range that we have system to be operated in. We need to make sure that we can control the system using the analog and digital means. We also need to make sure that we are able to support the system in not only the operating ranges, but to the disturbances. Now, Shannon's sampling theorem is a very fundamental theorem. So this is what it means. So if you have a signal and if this signal is varying, if I want to reconstruct this signal, what I need to do is I need to get one sample here. I need to get one sample here. Only then I would be able to represent this system or this signal very crudely. Again, I agree, this is not the accurate representation, but I'm able to find out the peak values. So I need to do the sampling at least at the twice the frequency of the signal just to capture the signal characteristics. That is called as Shannon's sampling theorem. Now, please understand that there is an issue which is something called as aliasing. So if you have signal that is varying, and if you have a sampling that is not at the Nyquist frequency, or you don't follow the Shannon sampling theorem, then what you will have is you will have spurious data that is actually not part of the signal, and that is called as aliasing. And because of the aliasing, what happens is you get additional characteristic or additional data that actually is not there, but that happens because of the interplay between the sampling frequency and the frequency of the signal. So aliasing is something that you would observe in a signal, something like this. So check this out. What we have is we have this baseline signal, which is at zero 0.8 hertz. And what I do is I basically sample it at a signal which is uh, at higher sampling frequency. I mean, which is at lower sampling frequency, which is at 0.2 hertz. So if I start doing that, understand, I capture this sample, I capture this sample, I capture this sample, capture this sample, I capture this sample, I capture this sample, which means the true signal is not captured, and I get something that is completely different than the original signal. That is the issue with aliasing. And how do we reduce the aliasing? Clearly, if I increase the sampling rate, then the aliasing would be reduced. If I add a low pass filtering and make sure that the low pass cutoff frequency is less than Nyquist frequency, which is also called as anti-aliasing filter, then I can reduce the aliasing. I will work out this example in next class. Let me quickly go through uh, what we are going to discuss in this chapter. So if you want to design a system for a particular bandwidth, please try to understand we have the control over the damping parameter, we have control over gain, and we have control over the external frequency or the natural frequency. So what we do is, if we are given a certain bandwidth, then what we can do is we can tune gain, we can tune the natural frequency, and we can tune the damping coefficients to meet certain bandwidth specs. And I will work through this example in next class. Uh, but these are the guidelines for bandwidth design. How do you design a mechatronic system to meet particular bandwidth specifications? And these are the steps that we will carry out. We will decide the maximum frequency. We will select the components. We will actually try to look at the flat spectrum. We'll design the controller, and we can design the digital control gains. And then finally, we'll integrate the system. Now, many a times, even though we design the system does not behave the way we want. So I don't know if you have heard this. No experiment is complete without an error. So what this error? This is the difference between what is being read by the instrument and the true value that instrument is measuring. So we want to minimize the error. It is not possible to completely eliminate the error, but there we have to minimize. And error analysis is tricky because many a times the true value is not known. We are sometimes using the higher order instruments or higher quality instruments to estimate the true value, but this may or may not be known. Instruments may contain some random errors because some variation in some parameters or random fluctuation in the temperature. Many a times the error may comprise of multiple variables, multiple input variables, state variable, response variables. And the system instrument may be made up with many components with complex interrelation. So there could be some dynamic coupling, there could be some multiple degrees of freedom response, and so on. So again, accuracy and precision are super important. Once again, what is accuracy? Accuracy is closeness to true value, and precision is nothing but repeatability. So whenever you talk about measurement errors, there are some deterministic errors or something called as systematic errors. Those errors are like offsets. They are going to remain constant. So once you know what that error is, you can actually take care of that error by proper calibration. A classic example is your bathroom weighing scale. If you step on it, and every time you step on it, the offset is 5 pounds, you know, hey, this machine has a 5 pound constant offset. So if my weight is 185 pounds, in reality I weigh 180 pounds. But sometimes what happens is there is some temperature variation, or it is responding to the humidity, or maybe it is responding to some random error. Then these are the factors we cannot ascertain. So basically these are the statistical parameters, and what we want to do is we want to specify this randomness by two statistical parameters. One is a mean value and the standard deviation. So deterministic errors that we can take care of. Random errors we can try to minimize, but basically we have to provide some statistical estimate on what would be the random error. And again, how do we combine different types of errors? If you think about combination of different errors, a simple example is if you have two vectors, one vector is R1 and other vector is R2. If R1 does not affect R2 and R2 does not affect R1, then the resultant is given by the Pythagorean theorem, which is square root of R1 plus R2 square. So square root of R1 square plus R2 square gives you the resultant error. So assuming these errors are independent or uncorrelated, that's what it means. in statistical sense, uncorrelated. There is no correlation. One error does not affect the other error. Then you can use a Pythagorean theorem to find out the total error. And this error combination is sometimes super duper important because we want to make sure that we have different types of errors in the system. But what is the cumulative effect of this total error? So what this error is based on these cumulative effects. But one thing that I want you to understand, sometimes the errors may be correlated, which means R1 may not be independent of R2. R1 and R2 would have some type of relationship, and at that time, this error analysis becomes difficult. So many a times, what we do is we specify something called as absolute error. We can sometimes we can say that sum of square root. So basically, sum of squares and square root. This is just like the Pythagorean error that we talked about, wherein what you have is you have individual errors. You you square those errors, add those together, and take a square root. So this is something like the Pythagorean error that I showed you. So it is an absolute error, and there is SRSS error. And again, here is an example that I will discuss in next class, and that actually talks about the error analysis. But once again, a brief recap. These are the important parameters in instruments and sensor rating: sensitivity, dynamic range, resolution, linearity, different types of non-linearities. And then what we have to do is, whenever we are trying to design the system, when we are trying to understand the system, we have to make sure that if the system is nonlinear, we have to make sure the operating range is linear. We avoid large responses, avoid loose components. Now, some of the definitions that are used in instrument ratings are zero drift, which is the output even if your input is zero; full scale drift, which is the variation of the instrument when you operate it at full scale. And then we can perform the error analysis, where the error is the difference between measured value and true value. There are different types of errors that we briefly talked about. Now, let me quickly give you an idea of what is precision. Precision is repeatability of instrumentation. So for an example, if you go in a clubhouse and you are playing darts, so this is your first shot, second shot, this is third shot. Ideally, you have to hit at the bullseye. Ideally, you have to hit at the bullseye, but you are hitting everywhere. So this is neither precise nor accurate. Now, if this is the bullseye and you are hitting the bullseye here, this is precise and accurate. And basically, if this is the bullseye, this is the bullseye, and you are hitting over here, this is precise but not accurate because you are close. This is the closeness of repeatability or closeness of measurement. This is repeatable, but this is not accurate. This is repeatable and accurate, and this is neither repeatable not accurate. So that's why you have this probabilistic analysis when you are going to look at the stochastic errors. And when you look at the probability, I will review this in next class, but there are two concepts that are very important. One is the density function, cumulative density function, and probability density function. Mean value is nothing but the average value or expected value when you have a discrete random variable. If you have a continuous random variable, we call it an expected value. You have the mean square value, which is the square of the means and expected value of the square. You have something called as the variance and standard deviation, and these random variables can be defined in the context of discrete random variables, or they can be defined in the context of continuous random variables. So I will talk about these two variations and these two differences in next class. And these are the properties of the random variables. If you have a continuous random variable, and again, what do we mean by independent random variables, which means the behavior of one random variable does not affect the behavior of the other random variable. But many a times you have dependent random variables, which means if you change x1, there is some effect on x2. Then sample mean, sample variance, these are for the discrete random variables. And then in the next class, I'm going to work out the example, the Gaussian distribution, central limit, and standard deviation. So we will also touch upon what we mean by statistical process control and what are the steps that are used in statistical process control. And I will review the concepts again. I will give you the precise mathematical definitions, and I'm going to work out the problems in next class. But this is chapter 5 from your textbook. And at this point, if you have the textbook, I would quickly ask you to go through the chapter 5 material and just make sure that we understand these simple concepts. So chapter 5 is a very simple topic. So in next class, I would work out the examples from chapter 5, and I will actually assign a homework that is based on the chapter 5. Unfortunately, I couldn't do an in-person class today, so there won't be a lab component. But I know that you have an assignment due tomorrow. So my suggestion to you would be, please complete the assignment, use this time to help each other out, and upload the solution to the assignment by tomorrow. And on Thursday, I would assign the next project. With that, I'm going to stop here, and I would be happy to answer any questions that you may have. Any questions from anyone? So we have covered chapter 2 in detail, and we have covered the basic theory of chapter 5. Next class, I'm going to review these concepts again, and then I'm going to work out the problem, and we'll finish chapter 5 and then move on to the controller analysis, control synthesis, and then work on the lab problems. Any questions from anyone? If there are no questions, I'm going to stop here, and I will see you on Thursday. I will upload the video lecture for this lesson, and I will see you on Thursday. Thursday's class would be in person. Thank you very much, and have a good day.